Okay, we're going to continue with our work on this homework, and the next problem, problem number 32. An electrostatic paint sprayer has a 0.2 meter diameter metal sphere with at a potential of 25 kilovolts that repels paint droplets into a grounded object. What charge is on the sphere? What charge must a 0.1 milligram drop of paint have to arrive at the object with the speed of 10 meters per second? Okay, so we have a 0.200 meter sphere, and that sphere is charged with a voltage of 25.0 kilovolts, which is equal to 2.5 times 10 to the 4 volts. And the voltage is equal to K, Q of the charge, divided by R. And so Q, which is the question, has to equal VR over K. And so that's going to be 2.5 times 10 to the 4th times R. Now it's radius, not diameter. So it's 0.1 divided by 8.99 times 10 to the 9th. You do the math here and you get 2.78 times 10 to the minus 7 coulombs of charge. Now the other question here is, what charge does the paint have to have in order for it to have this velocity? Well, what that means is the electric potential energy of the paint, which is QV, has to equal the kinetic energy of the paint, which is 1/2 mv squared. And so that means that 1/2 mv squared has to equal QV. And so we want to know Q. So Q is equal to 1/2 mv squared divided by V, where one V is velocity and the other V is voltage. Hope that's not confusing. And so the mass here was 0.1 milligrams, which is 0.1 times 10 to the minus 6th kilograms. We're talking about, we got to move everything into the right units. It's 10 meters per second, and that's divided by 2 and divided by the voltage, which is 2.5 times 10 to the 4th volts. If you do the math here, you get 2 times 10 to the minus 10 coulombs of charge. Okay, so the next few problems are under the heading of equal potential lines. And remember that the number of lines and the arrows are significant here. So you have to make sure the number of lines you draw and the arrows you put on them are significant. So let's look at this first problem, number 36, and in that I'll explain, what you have to do in terms of how the lines are drawn. Sketch the equal potential lines near a point charge of 1. So if you have 1 Q point charge, so by definition, a 1 Q point charge has 4 lines all going in, and the number 4 is the standard for a single charge of 1 Q, or 1.6 times 10 to the minus 19. And if it's positive, those lines have to be going out. Okay, so those are your equal potential lines. And with a positive charge, the voltage increases, or the potential increases by convention as you move toward the charge. So conversely, if we're going to draw the second one, which was a 3 charge, but it's negative. And so first of all, you have to have 3 times as many lines. So you have 1, 2, 3, 4. And then you have 2 extra for each one of these. So that you have a total of 9 lines. And then instead of moving away, they have to move to, all of these have to move toward the charge. And then the last change with the negative is the fact that the voltage, instead of increasing as you get closer, it decreases. So it increases as you go out. And so those are the three, that's the convention. Looking at number 40, it wants to know the interaction between these two particles, essentially. So you have a minus 3, and you have a positive 1 over here. And again, all of these are headed like this, and they engage 3 of the ones from the other side. And because it's positive over here and negative over here, the direction here is this way. And because this is greater, all of these, there are no other lines out here. They're all engaged at this point. And then you have an additional 7 lines that come out of this. And all the arrows have to go in, okay? I'm not going to draw all 7 of the arrows. And again, as you approach the positive, the voltage increases. So the direction of increasing voltage looks like this. Now let's move on to the last group of problems, which is problems around capacitance. Now, basically, the first one we're going to do is problem number 46. And in order to do problem number 46, you need to know that the charge of a capacitor is equal to the capacitance of that capacitor times the voltage that it's charged with. If you remember, a capacitor is essentially 2 plates that are very close together, and there's positive charge on one side and negative charge on the other side, and this device is used to store charge. And so if you charge each capacitor, the capacitance of a capacitor is calculated based on 3 factors. That is, what this capacitor is made up of, which is the combination of something called the dielectric and the permittivity of the capacitor, and then the area of the 2 plates divided by the distance between the 2 plates. And so a capacitor is based on its composition, its area, and the distance between the 2 plates. And this tells you how much capacitance that it has, the ability to hold charge. And then if you multiply that by the voltage that's used to charge this, you know how much charge is stored on these plates. And then this problem asks the question, number 46, asks the question, what is the charge stored in a 180 microfarad capacitor when it's charged with 120 volts? Okay, so this first one's very simple. The charge is going to be, it's 180 microfarads, which is 1.8 times 10 to the minus 4 faradays. 180 microfarads is 1.8 times, and then the voltage is 120 volts. And so if you do that math, you get 2.16 times 10 to the minus 2 coulombs. So there are that many electrons, the equivalent of that charge on that capacitor, or 21.6 millicoulombs. Let's do another one, 49. 49 is a very similar problem. It says calculate the voltage applied to a 2 microfarad capacitor when it holds 3.1 microcoulombs. Well, you just rearrange this in order to find the voltage. So V, if you rearrange this, is going to equal Q divided by C, which is going to equal, and Q is 3.1 times 10 to the minus 6, and C is 2.0 times 10 to the minus 6. So you end up with 1.55, I think it was. Yeah, 1.55 volts. Okay, number 52. Number 52, what is the capacitance of a large Van de Graaff generator terminal given that it stores 8 millicuries of charge at a voltage of 12 megavolts? So the question is what is the capacitance? Again, you rearrange this, and capacitance is equal to Q over V, which is equal to 8.00 times 10 to the minus 3 coulombs divided by 1.2 times 10 to the 7th volts. 12 megavolts is 1.2 times 10 to the minus 7 volts. If you do the math there, you get 6.67 times 10 to the minus 10 Faradays, or 66.7 nanofarads. The next one is a problem to calculate using the other formula that I showed you up here, right here. The next problem, problem number 53, says that find the capacitance of parallel plate capacitor having plates of an area 5 separated by 0.1 with Teflon. Now what you need to know with Teflon is the permittivity, or K. And you can look that up in the book. So C is equal to, this should have been E0 by the way, C is equal to K, which you can look up in the book, E0, which is in the chapter, and it's a standard, A over D. Well, K for Teflon is 2.1. E0 is 8.85 times 10 to the minus 12. And then the area they gave is 5 square meters. The distance between the plates was 1/10 of a millimeter, or 1 times 10 to the minus 4 meters. And so if you do the calculation there, the capacitance is going to be 9.29 times 10 to the minus 7 Faradays, or 0.923, let's say, microfarads. 0.93 microfarads. 55. A prankster applies 450 volts to an 80 microfarad capacitor and then throws it at someone, and it burns them. And it burns approximately 0.2 of a gram of flesh. What is the temperature increase of the flesh? Okay. If you look at that, what you're looking at is the energy impact of a discharge of a capacitor. And the energy, if you look in the book, you'll find that the energy of a capacitor is equal to its capacitance times the voltage squared divided by 2. Okay, the charge is basically, the charge is equal to this, okay? and the energy is equal to this, and you can look in the book at how they derive that, okay? And so if we take, and what they want to know is the change in temperature, okay? So if we take this, the capacitance is 80 micro, so that's times 10 to the minus 5 times the voltage squared divided by 2. Okay, so that's the energy discharge into the flesh. And so they want to know what the change in temperature is. Well, that's got to be equal to mc delta T, and this is what we want right here. And so if we divide this 8.00 times 10 to the minus 5 times 450 squared, if we take and divide that by the mass, which is given, the flesh was 2 grams, so we need to make that times 10 to the minus 3 to make it kilograms. And then from the book, the specific heat of flesh is approximately 3,500 joules per kilogram degrees centigrade, and that's going to equal delta T. And delta T then is going to be 11.6 degrees centigrade as a temperature change. Okie doke.